Hello and welcome to my carbon sequestration presentation. Today I will be discussing the capture of carbon emissions and sequestration in geologic formations. So, what is geo-sequestration? Carbon geosequestration is also known as carbon capture and storage, and as the name cunningly suggests, involves the capture and storage of carbon, essentially taking carbon from a source point and stuffing it underground. The IPCC describes it as the process whereby CO2 is separated from industrial and energy-related sources, then transported and stored in a location isolated from the atmosphere. CO2 emissions are dominated by human actions, predominantly energy generation via the combustion of fossil fuels and industrial processes, transport and land clearing. Although natural sources of carbon emissions do exist, such as volcanic activity, they are overshadowed by anthropogenic contributions. So how does geosequestration work? Well, geosequestration, carbon capture and storage, also known as CCS, requires the employment of technology to first capture carbon emitted post or pre-process, then concentrate it into a transportable form, transport it, and from there it can be stored underground in geologic formations. In terms of source capture, not all sources were born equal. Some emit significantly higher concentrations of CO2 than others. And in terms of practicality, stationary sources such as power plants and industrial processes show a simpler potential for implementation of CCS mitigation than do mobile sources such as vehicles, for obvious reasons. The 2005 IPCC CCS report suggested that starting with high-emitting stationary resources would be the best avenue for significant impact. So there are three primary approaches to CO2 capture: post-combustion, pre-combustion, and oxy-fuel combustion. Post-combustion involves the separating of CO2 from flue gases produced by combustion of primary fuels, coal or natural gas, in air, which is largely nitrogen, using a liquid solvent. This method tends to have a small proportion capture of around 3 to 15%. Pre-combustion involves processing the primary fuel in a reactor with steam and air or oxygen, and this process produces a mixture of carbon monoxide and hydrogen. Further, hydrogen and CO2 is produced by reacting carbon monoxide with steam, and this second process results in a mix of hydrogen and CO2 that can then be separated into a stream of each of CO2 and nitrogen. This process typically produces higher concentrations of CO2, around 15 to 16%. The beauty of this albeit complex and costly process is that the separated hydrogen can be used itself as a combustible energy source. Oxy-fuel combustion involves using oxygen rather than air in the combustion of the primary fuel. This produces a flue gas which is largely water vapor and CO2. The water vapor is then removed by cooling and compressing, leaving behind the CO2 at a concentration of more than 80%. Once captured, the carbon is then compressed into a fluid called supercritical CO2 and pumped into an appropriate geological formation. Rock formations best suited to this application are found deep, like 900 meters deep, underground, are porous enough for the pumped CO2 to move into, and have a cap rock to keep everything where it needs to be, basically separated from the atmosphere. Typically, these formations are saline aquifers, unminable coal seams, depleted oil and gas reservoirs, or, as has been done since the 1970s, used in enhanced oil recovery. Saline aquifers are reasonably common and currently aren't known to have any suitable use for exploitation by humans, aside from their probable carbon sequestering potential. They're also believed to have the largest storage capacity. Unminable coal seams, again without any use for us as exploitation sources, may prove to be a viable point of CO2 deposition. Enhanced oil recovery has, as mentioned before, been used since the 1970s to help with oil recovery in mature oil fields, and this technology similarly may provide a solid or sound deposition point for captured carbon. So what are the advantages and drawbacks of geosequestration? Well, geosequestration is still largely in its developmental stages. However, some more eager proponents suggest that its application could mean that CO2 emitting processes would be able to go on unhindered, keeping with the aspirations of the status quo and neoclassical economics mantra of non-stop growth. This can be seen as either an advantage or a drawback, depending on which side of the debate you are situated. So So looking at advantages, this method has already been used to an extent in enhanced oil recovery, so it's not an entirely untested concept. It also can be, in theory, applied to power plants, refineries, steel or cement manufacturer, fertilizer production, and so on. Anything stationary, more or less. Drawbacks include that the separation of CO2 is a high energy and therefore high cost procedure, and this can be justified as offsetting future impacts and costs of CO2. However, cost is generally always seen as a drawback. On the environmental front, leakages could contaminate important aquifers, and the pumping of CO2 underground, as pointed out by Zorbach and Gorelick, has the potential to cause earthquakes. Kind of a big deal. So how important is geo-sequestration in the overall effort to combat climate change? Well, in conclusion, although at the outset the concept of capturing and storing carbon may seem a little far-fetched, it may likely prove, as the IPCC suggests, an indispensable component of climate change mitigation technologies to be used to evade climate change effects. Concerns naturally arise over the implications that this technology could, in essence, allow or even endorse the continuation of business as usual unhindered, which leads one to highlight concepts such as the Jevons paradox. But it is important to keep in mind that this solution of capturing and storing carbon is long-term, with storage of carbon being a long-term process and a one-way transaction. Once captured, the carbon is intended to remain stored for hundreds of years at a minimum. The capture and sequestration of CO2 from emitting sources is only one slice of the mitigation pie, and it would need to occur in conjunction with other mitigation methods such as the shift to a dominance in renewable energies in order to meet the 2-degree target. Therefore, despite the drawbacks such as cost and potential environmental impacts, this method has real potential to aid the reduction of atmospheric CO2 concentrations on the journey to a stable future. Thank you for listening. Please enjoy this list of references.